Today we're going to continue with geometric sequences, and we're going to do some of the same things that we did with arithmetic sequences, where we're looking for patterns to help us develop the explicit and recursive formulas. So let's start by looking at a geometric sequence. There's a couple of important pieces of information for us to have. First of all, we have our initial term or starting value, and in this case that's a 3. And then we need to know our common ratio. In this case, the number we're multiplying by to get from one term to the next is 2. And this 2 is going to become extremely important in our pattern. Starting with our initial value, if I take a look at what it takes to get from the first term to the second term, we can see that we're multiplying by 2. To get from the first term to the third term, to get from 3 to 12, I'm multiplying by 4. From 3 to 24, I multiply by 8. And even our next term in the sequence, let's add one more. Our next term would be 48. To get from 3 to 48, we'd multiply by 16. So let's take a look at those specific numbers, the numbers that we multiplied by. We have 2, 4, 8, and 16, and I'm even going to come back and say to get from 3 to itself, we multiply by 1. Well, these are all not just multiples of 2, these are powers of 2. 2 is the same as 2 to the first power. 4 is equivalent to 2 to the second power. 8 is 2 to the third power. And 16 is 2 to the fourth power. Even back here, 1 is also a power of 2 because anything to the 0 power is equal to 1. So that's 2 to the 0 power. If you take the time to look at what pattern is starting to develop, you can see that to get to my first term, I multiplied or took my common ratio to a power of 0. To get to my second term, I took my common ratio to a power of 1. The third term came about by multiplying by a common ratio to a power of 2, the fourth term to a power of 3, the fifth term to a power of 4, and so on. So if you notice, the powers on our common ratio are always 1 less than the term number. So if I came out to say the 10th term, I would multiply by 2 to a power of 9. My power is always 1 less than the term number. Well, we originally started by multiplying our initial term by that value, right? So if we're going to look at a pattern here, we always multiplied. We started by taking 3. Let me change colors back. We started with 3. And then every single time we wanted to go to a new term, we multiplied that 3 by our common ratio to a power that's 1 less than the term number. Remember, in sequences, n refers to the term number itself. So 2 taken to a power that's 1 less than the term number multiplied to our initial term always gives us the term itself. So if I wanted to find the fourth term, I would take 2 to the third power and then multiply it by my initial term 3 to get that specific term in my sequence. Well, let's kind of clarify this. Let's look at a few more, and then we'll come up with a general form for our explicit formula. Let's take a look at this specific sequence, 2, -6, 18, and -54. We've seen that before in one of our previous videos, and we know that our initial term is 2, and our common ratio is -3. The relation in this sequence is I'd always start with my initial term, and then I'd take the common ratio and take the common ratio to a power that's 1 less than the term number. That would equal any term in the sequence. Remember, a sub n refers to any term in the sequence. In our second sequence, I start with 16, that's our initial term, and our common ratio this time might be a little bit tricky. Remember, in geometric sequences, we always multiply, we never divide. So instead of saying we're dividing by 2, we'd rather say we're multiplying by 1/2 or 0.5, whatever your preference is. So to find the relation in this sequence, we'd say to find any term in our sequence, we'd take 16 and we'd have to multiply that by 1/2 to 1 less than our term number. If I can get this to right. Sometimes technology is not very nice, right? But that kind of gives us a general relationship between all the terms in a sequence. So let's turn that into a general explicit formula for geometric sequences. We said to get any term in the sequence, we took the initial term and multiplied that by our common ratio taken to a power that's 1 less than the term number we want. This is our explicit formula for geometric sequences. And again, an explicit formula will help you find any term in the sequence without having to go through the pain of actually writing out all the terms of the sequence. So if I wanted to find the 200th term in the sequence, I would use the explicit formula to do just that. A recursive formula is notation based only. It's only going to tell us what the pattern is that gives us our sequence. So recursive formulas, if you remember from our last video, have two parts. They have an initial term. Oh wow, that's really bad handwriting. An initial term, a sub 1 equals whatever your initial term is. But then we have to explain the pattern. To find any term in the sequence, we take the term before. If n is our term number, then n minus 1, that's a 1, would give us the term before, and we're going to multiply that by our common ratio. So take a term, multiply it by the common ratio, that gives you the next term in the sequence. This is what a recursive formula looks like, and it will only tell you the pattern to give you the sequence itself. Let's take a look at one example and then we'll call it for today. Here we have a geometric sequence. Our initial term, you can see, is 4, and our common ratio is -4. If we want to write an explicit formula for this sequence, we start out with a sub n equals 4, our initial term, times our common ratio. And it's extremely important to put negative numbers in parentheses, especially when you're taking that number to a power on a calculator, to the n minus 1 power. And if I had to write the recursive formula, I would say our initial term is 4, comma, and to find any term in the sequence, we take the term before, a sub n minus 1. Oh, wow. Let's see if I can write that a little better. Apparently the software is not catching up to me. Anyway, a sub n minus 1, I promise you that's what that's supposed to say, times by our common ratio of -4. Take a term, multiply it by -4, that's how you're going to get the next term in the sequence. So if I have to find a sub 100, or the 100th term in the sequence, I would not want to use the recursive formula because that doesn't help me actually solve for anything. It describes the pattern. I would use the explicit formula. I would say a sub 100 is equal to 4 times -4 to 1 less than the term number I want, so to the 99th power. Now when I put this in a calculator, order of operations says that exponents has to come before multiplying, so I would put -4 in parentheses to the 99th power, then I would multiply that total by 4. And actually this is going to give us a number that's too big for your calculator screen. It's actually going to be too big for me to write on this screen because it's going to have upwards of 16 or 17 digits to it. So we won't actually solve this one, but this kind of will help you know how to write it so you can put it in your calculator later. Okay, I think let's call that good for today. I hope you have a fantastic rest of your day, and I will of course see you next time.